welcome to my channel. Today we are going to dive into how to make a game using three algorithms. The game is going to be coded in Java. The pattern goal we are trying to achieve in this game is with an empty space in the center of the board with 1, 2, 3, 4, 5, 6, 7, 8 going around it. And it's the game of 8 puzzle game which we used to play back in the day. And we are going to make the game using three algorithms. They are uniform cost search, best first search, and a star algorithm. And we are also going to record the statistics of how the algorithms are working, which I'm going to record them myself after coding. And then let's dive on to the first one, uniform cost search. We'll be presenting the code for solving the 8 puzzle problem using uniform cost search algorithm. This is a common algorithm used to find the least cost path to the solution of a problem when all actions have equal cost, which in our case is simply moving tiles in a puzzle. Let's dive into the two main files, uniform cost search.java and puzzlegui.java. First, let's start by looking at the uniform cost search.java file. The program begins with defining the puzzle state class. This class represents the current state of the puzzle. It holds a 2D array board to store the positions of tiles along with variables 0 row and 0 col to store the position of the empty tile, which is 0 in our puzzle. And the constructor initializes these variables, and we have a helper method, deep copy to clone the board, and then the board state. And next, the compare to method is implemented to allow our priority queue to order the states by their cost, ensuring that the least costly states are expanded first. And then the isGoal method checks whether the current state of the puzzle matches the goal configuration, which is a 3 by 3 grid where the tiles are in a specific order. In the getSuccesses method, we generate all valid moves that can be made from the current state. For each valid move, we create a new puzzle state, increment the cost by 1, and push it into the priority queue. The isValidMove method ensures that we don't move the empty tile out of the bounds, and then the search process uses a priority queue to always expand the least cost state first. Once the goal is found, we backtrack to generate the solution and store it in a queue like this, and then right around here the solveUCS method handles the main loop where the algorithm runs, finding the solution and returning the results, including the solution path, the number of nodes visited, iterations, and the runtime of the algorithm. And I am going as slowly as possible. And this all interacts with the puzzle GUI, which we will go now. And this file is responsible for creating the graphical interface, which will allow the users to interact with the puzzle and view the solution. And we start with defining the board size, which is 3, since it's a 3 times 3 puzzle. And the constructor initializes a grid of buttons representing the tiles of the puzzle. Each button is labeled with the number corresponding to the tile, and there's a JText area to display the statistics like the number of nodes, visited iterations, and runtime. Yeah, and the get start board, which is right here, method fetches the current state of the puzzle board from the buttons array, converting it into a 2D integer array to be used by the algorithm. And the puzzle GUI constructor takes the starting board, solution path, statistics, and displays them. The next step button right here allows the user to progress through the solution path one step at a time. After the puzzle is solved, the statistics are displayed in the JText area right here. And in the main method, we set an initial state for the puzzle, like right here in the main method, and call the UCS solver and pass the solution and stats to the GUI to display them interactively. Now let's run the code to see how everything works together. We will solve an 8 puzzle with an initial state like this, and after running the program, the puzzle will be solved step by step like this. And yay, we solved it. And we can see the statistics including nodes visited, iterations, runtime, and we can see that the uniform cost search algorithm efficiently finds the least cost path and with the GUI, and we can track the progress of the solution interactively through this. And I hope this walkthrough of the code has clarified how the uniform cost search algorithm and puzzle GUI work together. And I will run this code several times to record the statistics. We will do best first search algorithm code. Now we will solve the 8 puzzle problem using the best first search algorithm. Let's get started. First we have the puzzle state class. This represents a state of our puzzle. It includes methods to calculate the Manhattan distance heuristic, generate successor states, and check if we have reached the goal state. Next, let's move on to the solve BFS method in the best first search, and it's right down here. Yep, right here. This function initializes the puzzle state, uses a priority queue to explore states with the best heuristic, and builds the solution path once the goal state is found, right around here. Notice how we use a priority queue to prioritize states with lower heuristic values, making our search more efficient. In the puzzle GUI, to make our solution more interactive, we have a GUI built with swing right here. The puzzle GUI class displays the puzzle and allows users to step through the solution. Let's see around here, making the board, making it the zero blank and everything. So now let's run the program and solve the puzzle. Right here, as you can see, there is a blank space, and I will try to move through as quickly as possible. We are almost there. Yay, we solved it. And that's how you solve the 8 puzzle problem using best first search in Java. So I'll run the code with different start boards to have our statistics in the end to display. Thank you. Now we will do the A algorithm. For a quick recall of the problem, in the 8 puzzle, the board starts in a scramble state. Our task is to arrange the tiles in a specific goal state with the empty space represented by 0 or blank in the center of the board. Now for the third algorithm we are going to be implementing is the A star algorithm, which will help us find the shortest path from the initial state to the goal. It does this by considering both the cost to reach the current state and an estimate of the cost to reach the goal using a heuristic. So as you can see the formula right here, A star works by evaluating states based on two components, the G cost, which is the number of steps taken to reach the current state, and the H cost, which is heuristic, which is an estimate of the remaining steps to reach the goal. The total cost is calculated by adding both, and the state with the lowest total cost is expanded first. So let's dive into the code. We can start with the puzzle state class, which represents a specific state of the puzzle. This class stores the current configuration of the puzzle, the position of the empty space, and the cost values for a star. So as we go down right here, the heuristic function calculates how far the current state is from the goal using Manhattan distance and linear conflict. And then right down here is the linear conflict, and right around here is the get successors method, which generates the possible next states by moving the empty space around the board like this. And the isGoal method checks, did I move up? So the isGoal method checks if the current state matches the goal state. And then now let's see the A star solver, which is down here. It begins by initializing the puzzle with the start state and then uses a priority queue to explore the most promising states first. So a priority queue is used to always expand the state with the lowest cost G plus H right around here. Once the goal state is reached, we reconstruct the solution path by backtracking from the goal state to the initial state. And then we have the main method, which runs the algorithm solving the puzzle and displaying statistics like nodes visited and the total time taken. So I'll go slowly. And we have reached the end of the file. So to make things interactive, we have created a graphical user interface with the puzzle GUI class. It displays the current puzzle state with buttons representing each tile. The board is displayed as a grid of buttons. Each tile is a button and the blank space is left empty. So users can step through the solution path using a next step button, which is right here, and which shows one move at a time. And the board is updated by changing the button labels, showing the user how the tiles move. It's right around here. And then that's it. So now let's see it in action. And Yep, and it will take quite some time as the blank space moves around to make the pattern. And yay! So here is the statistics, and we can see the number of nodes visited, iterations, and runtime. And that's how, my friends, A star algorithm can be applied to solve the 8 puzzle problem. I will run the code 5 times from my side and record the statistics. And let's go back to the statistics chart. Based on the statistics and comments so far, if you need optimal paths and have a suitable heuristic, A star is generally the better choice. Like here, if you are more focused on speed and can tolerate non-optimal paths, best first search might be preferable. UCS is the best when you need guaranteed shortest paths without using heuristics. Ultimately, the choice depends on the specific requirements of your problem and the quality of the heuristics available. And that's it. Thank you for watching.